Hi friends, welcome to today's tutorial. Today we shall be talking about the determination of maximum moment for a series of concentrated moving load on a simply supported beam. Now we must understand that in designing of dynamic loads, we basically make use of the influence line to determine the maximum moment at any point when dealing with dynamic or transient load. But today we want to concentrate on a series of concentrated moving loads, basically on a simply supported beam, determining the position of maximum bending moment at any point. And also, we are still going to be talking about the determination of the maximum bending moment on the beam. Okay, so talking about the maximum bending moment at a point and the maximum bending moment of the beam, we are going to be dealing with each of these separately. Now let's start with the maximum bending moment of a series of concentrated load moving along a simply supported beam. The first step in determining the maximum bending moment of a series of concentrated load on a simply supported beam is to determine the resultant force or resultant load. In other words, acting on that particular moving load. And this is the configuration of this load. We have it as this, we have it as this. Okay, let's assume this load is not a symmetrical load. Hence, it's not a symmetrical load. What it means is that the center of gravity of this load cannot be at the center. Okay, if you are having series of concentrated load that are not symmetrical in nature, you don't expect the center of gravity to be at the center of the span. Okay, so let's say we have this. Let's call this one P1. Let's call this one P2. We call this P3 and P4 respectively. Okay, so if we have this set of concentrated loads, we first of all we have to determine the center of gravity of this load. But let's assume that we have our center of gravity to be somewhere around here. We do not know, but let's call it somewhere around here. The center of gravity of the resultant load. Let's find it somewhere around here and let's call it bar X. So that center of gravity is bar X. All right. And let's call this our moving load, the total length of it to be L. Okay. To here. So what it means is that the center of gravity is L minus bar X. Okay. From this end of the load. So the center of gravity is L minus bar S from the other side of the load. So now the maximum moment of this particular series of moving load on a simply supported beam will be gotten when this load is placed at the center of the beam in such a way that the distance between the resultant load and either of P2 or P3 is placed to coincide, okay, to coincide with the distance between P2 and P3 over 2. What I mean is, this is the distance between the resultant load and P2. There's a distance. Can we just call it something so for explanation, for the purpose of explanation? Can we call it K? Okay. Can we call it K? Okay, let's call it K. All right. K. Now, the other side of it, which is from P3 to the resultant load, let's call this one K prime. K prime, okay? Let's call it K prime. All right. So if you look at the board, we are talking about K and K prime. So the resultant load, the distance from the resultant load, RL to P2 is K, while the distance of the resultant load from P3, we are calling it K prime. Or if you like, let's call it K1. Let's call it K1. Okay. So we have K1 and K prime. So what we are saying is that the maximum moment of this set of concentrated load on a simply supported beam is gotten when uh, the vehicle is placed, or all these loads are placed in such a way that uh, the center line between uh, K over 2, or the equidistance between the center line of K is placed to coincide with the center line of the beam. So what we are saying is that dividing K into 2 and place that center on the center line of the beam, or dividing K1 into 2 and place that center at the center line of the beam. So when you do this, each case will produce moment, but it's now left for you to do a trial and error to get which of them will produce the maximum moment for this simply supported beam. So what we are saying in the effect is, uh, let's put our loads we have here, uh, we have here, we have here, we have here. So what we are saying is, if there becomes our resultant load bar X, all right, we intend to determine the maximum moment of this load on a simply supported beam. Okay, we know that from here, these are resultant load. We know that here is K, here is K already. We know here is K. So let's call here K. Okay, so what we are saying is that K, the center line between here is somewhere here, which is K over 2. Here becomes K over 2, K over 2. We are saying that that distance should be placed at the center line of our beam. Let's call our span of beam to be L. Okay, here's L over 2. So let's say total span of this beam is L. All right. All right. So, well, this is what we are trying to say. Mm, this is P. All right. So what we are saying is, when the load is placed in this way, you can determine the maximum moment of this moving load. And that maximum moment is likely to be either under the load P, or either under the load, either under the load P2 or under the load P3. Okay. So if that is the case, this P2, this P3, and this P4. All right. That is the first case. Now, the second case is when, like I said, you place the load on the simply supported base so that it coincides in such a way that K1 becomes our target. If we do that, we are going to have this load as this again. We have this load as this again. We have it K1, K2, and here we have the resultant load RL. Then we have here to be P3, and the last of it is P4. So now, if you look at it now, we have all this, we have the resultant load. Now we want to deal with K. The next thing we're going to try out is using K1. This is K1. So I'm going to look for the center of K1, this center of K1, and I will ensure that that center of K1 coincide with the center of my simply supported beam. If you position this load on this beam this way, here will be, here is K1 over 2, here becomes K1 over 2. So once the load is stationed this way, the next thing you are going to find out is here, remember our beam, L over 2, L over 2, total span is L. Okay, so this is what we are going to do. So when you do this, you can now, uh, you can see now that you now determine the moment at the moment at point load P2 and the moment at point load P3, and find out which of them will give you the maximum moment. Whichever give you the maximum moment becomes the one to be taken as the maximum moment on the beam. All right. Same thing also when you place it on K. You find the moment at point 2, find the moment at point 3. Whichever one gives you the highest value becomes the value for the maximum moment on the beam. All right. So this is how we determine the maximum moment of a series of concentrated moving load. Of course, we can determine the resultant load of the vehicle, which is quite easy, like you can see. Once that is done, you can go ahead to solving that problem. So we are going to take an example of this. We'll just pick a value, place it on the P's, the P3 or the P4, make it P5 as the case may be. So whichever we intend to do, we'll do it so that we can obtain the maximum bending moment on this beam, simply supported beam. Okay. I'm going to take a very critical example that is not going to be too simple. But when your loads are symmetrical, it becomes very simple. Let's take something a little bit complex, whereby we have the loads to be different, and we have the distances to be quite different. So whichever case we are going to pick for an example. So let's pick the first one. Quickly, let's look at a situation. The first situation we're going to look at is, let's see how we can do. We can look at this. Let me make the first one. Now let's consider a system of concentrated loads. We'll consider a system of concentrated moving loads for this example, determining the maximum moment. All right. So let's take a load of this. Let's consider a of system of concentrated moving load. So if we do that, let's say we have it as this. Okay, we have this as this. I'm not drawing it to scale, so don't mind my drawings. All right, we have 1, we have 2, we have 3, and we have 4 and 5. All right. So now we have a system of 5 concentrated moving load. These loads are going to be moving through a beam that is simply supported. And now let's assume that we have these loads to be P. Let's call it P1 just for the purpose of explanation. Let's call it P1. and let's call it P2, P3. Sorry, let's just name it again. We call it P1, call it P2, call it P3, P4, and P5. All right. So these are the loads we have. Let's assume it's a vehicle that is moving. It's a moving vehicle, and this vehicle is intends to move on a simply supported beam. Now let's look at the distances between the load. The first distance we have the first one to be, we have here to be 3 meters. Let's call here 3 meters. All right. Okay, let's call here, what are we going to call here? Let's say, okay, we have here to be 4 meters. All right. The next one, let's say we have the next one to be, we can call that one 1 meter. Then the last of it, let's just say we call here 8 meters. Okay. So the total length, let's total it to get the total length of this. This is 16 meters. 16 meters. Okay. So now we have the total load to be 16 meters P1 to P5, where we have it at 60 meters. Now this load is expected to run on a simply supported beam. So since it's expected to run a simply supported beam, the first thing we are going to do, we need to obtain what? The resultant load and the center of gravity of this resultant load. Now if we assume, let's make an assumption. All right, let's assume anywhere around here, we can just say that we know that the resultant load arrow is acting somewhere around here. All right. So if we have the resultant load arrow acting at that point, we needed to obtain the distance. Okay, very, very important. We can easily calculate the total resultant load. The total resultant load is a summation of the individual point loads. So we can say total resultant load RL becomes P1, P2, P3, P4, and P5. Okay. So let's assume our P's to be equal. If we assume our P's to be equal, we can say where P is equal to P1, and P1 is equal to P2, equals to P3, equals to P4, and is equals to P5. So if P is this, what it means is total resultant load, total RL, will be equal to, we have 5 P's there, so it becomes 5P. All right. So we know what our P is. The next thing we are going to determine is the distance of our P, our RL from this end. So the center of gravity is here, but let's find out the center of gravity, which is the distance. So if we want to do that, we can simply just take a moment about any point along this load. All right. So if we do that, for example, let's take a moment about, let's call here point 1. Let's call here point 2. So if we take a moment about point 2, we'll say summation of moment about point 2, let it be 0. We'll have it as RL, okay. We'll have it as RL equal times, Okay, let's do it this way. Let's say summation of moment about point 0.1 so that we can get x. Okay, let's say summation of moment about point 0.1. If we do that, we'll have RL times bar x. All right, it becomes P2 P2 times P2 times 3. All right, it becomes P3 times 7, or 7 times P3. We now have it as 4 times P4 times P4 P4 times 8, then plus P5 times 16. All right. So if we do that, we'll have RL times bar X. That will give us where P is equals to P1, P2, P3. What it means is that we're going to have 3 plus 7, which is 10, plus 8, 18, 18 plus 18 plus 16. That will give us a 34. So we have a 34p. 34p. So if we do that, we'll have that bar S is equal to 34p over 5p. All right. Now remember, taking down the moment, we are not really interested in the sign of the moment because this is just a load that is moving. We're not looking at the gravitational impact of this load. So the negative sign is not really considered at this point, because if I decide to put my negative sign, it means that my RL will become negative 5p. But we're not interested in the stability at this point. We are just interested in getting the position of the center of gravity, not necessarily on the stability. So my RL is taken as 5p. All right. Once the vehicle is on the ground, it becomes stable. Once it's on the beam, it becomes stable. Okay. So we have bar S to be this. And if we do that, we will discover that our bar X, our bar S becomes 6.8p meters. So 6.8p meters away from this side of the beam. If you minus it from the total length of the vehicle, you discover that the other side is 9.2. Okay, if you remove 6.8p from 16, you have 9. All right. Sorry, there won't be p here, of course. If you remove 16 from 6.8, you have 9.2. All right, so this is what we have. This is center. So once we have been able to get the center from our previous discussion, all we have to do is to quickly insert it on the beam and get the maximum moment on the beam. Let's do this one quickly and let's obtain the maximum moment. So let's obtain the maximum moment. So quickly, the next thing we're going to do is to determine to get the maximum moment of this beam. Now, the first thing we'll do, let's draw the vehicle on it. So we'll say this is our dynamic load we have here. So we are saying that from here to somewhere, yes, 6 meters. Remember that we have here to be 3 meters. We have here to be 3 meters. Okay, this P1, this P2. So we have here to be 3 meters. Our center of gravity, which is the point where the resultant load is acting, is around here. So we have here to be 5p. Okay. Of course, we know that from here is 4 meters. All right. Here's 4 meters, which is our P3. We have P4. And the last of it is our P5. Okay. So when you look at it, you can see can say it from this point that all the values are already stated here. We have P3. So now the resultant load is P5, is 5P. And if we do this very well, you'll agree with me that from here to here is 4 meters. From here to here is 4 meters. Okay. Here is 3. So what is left here is around, so from here to here is, yes, 3.8. Okay. So that place is 3.8. So the first thing we are going to do is to place this vehicle in such a way that the equidistance between the resultant load and P is placed to coincide with the center line of the beam. So when we do that, we have the beam as this. This is our beam. This is our beam, simply supported beam. So I'm going to place it immediately. These are center line of our beam. So we're going to place this vehicle in such a way that the distance between this resultant load and P2 is placed at equal distance in such a way that it coincides with the center line of our beam. So we'll have it as this. Okay. This is our resultant load. Let's put it this way. Our resultant load is 5P. Okay. Now, of course, here is 4 meters and here is 3.8. So what we should be having left here should be 0.2. Okay, so very, very small value. So let me just try to indicate it to scale, but whatever we are doing is not to scale. Our drawing is not to scale, so let's call it 0.2. So if that happens, here is 3.8. So we are splitting 3.8. If we split 3.8 here, we have here to be 1.9, 1.9, okay? 1.9, 1.9, okay? So since we have here to be 1.9, remember that here remains our P2. Here's load P2. After P2, the next one we have is P1. Here's our P1. And we already know the distance is 3 meters. Okay. So the distance is 3 meters. Here is 1.9, like I've said earlier on. 1.9, 1.9. All right. Now we have P1, P2. We have, let's look at P3. P3 will be somewhere here. Okay. Here's P3. Let's get our P4. Let's call here our P4. P4. Of course, we know that P4 and P3 have a distance of 1 meter. So here is 1 meter. All right. Or let's just put it 1 meter. Then the next thing we're going to see is the last of all the load, which is P5. So these are P5. P5. And we know that our P5 here is 8 meters. Okay. So we have successfully, let's put the support here so that we can get what is left over. Okay. Remember that here is, we are dealing with a beam which we have not stated the span. Now let's assume that our beam is of a span of 20 meters. If our beam is on a span of 20 meters, we know that the middle of that beam will become 10 meter on either side. Okay, so let's say our beam here, 10 meters on this side is 10 meters. So we have this beam as 10 meters, 20 meters span. Now, if we have P1, P2, P3, P4, P5, we've got in the center. The center of gravity is 6.8 meters away from this left hand side. and 9.2 from the right hand side corner. And we've been able to do the first arrangement by placing uh, the equidistance between the resultant load and P2 at the center line of the beam. With this, we can now calculate the moment on this beam. Okay. Let's fix the value from P1 to the left-hand support. Let's call the left-hand support support A, and that of the right-hand side support B. Okay, let's find out the distance between support A and the load P1. If we can get distance between support A and load P1 so that we can easily calculate moment. The distance between support A and P1 is this 10, is 1.9, which is 4.9 minus 10 minus 4.9. We can do it from there. All right. So let's say 10 minus 4.9. So 10 minus 4.9 will give us 5.1. So what it means is that from here it's 5.1. All right. Now let's do the same for the other side. We have 10. So this one becomes 10. Let's see what happens here. This becomes 10 meters. Yes, 8, 1, which is 9. Yes, 8, 1, which is 9. This 10.9 plus 1. This is 11.1. Ha ha ha. You can say that 11.1, that is the total length, meaning that load P5 is already out of the support. That is what it means. 11.1. So definitely load P5 is going to go out of the beam. So if that happens, it means that load P5, you are not going to be there. You are going. We already have 10 meters. So what we'll be working is just this. Okay. So we'll be much more interested in the remaining ones. So load P5 is already out of the game. All right. It's already out of the game. It's out of the game by some fractions. Okay. So from the inside, since we have it as 11.1 as against 10, okay, it's already out by 1.1. So this here, uh, this load is already out of the beam by 1.1. All right, it's already out of the beam by 1.1. So if it's out of the beam and here to here is 8 meters, what it means is that 8 meters minus 1.1, we are going to have 8 minus 1.1, this is 9, 7, 6. So what it means is that from here to the ending of the support becomes 6.9. All right. So if load P5 is already at, we'll be having 6.9. So we only have 6.9 within the beam for the design. Okay. So let's go over and let's see how we can analyze this and design it to get and get the maximum moment on this particular beam. All right. So let's go over. So quickly, let's determine the maximum moment. Like I said in earlier on, I said the moment we have P1, P2, P3, P4, and P5, which is totally out of the beam. All right. So P5 is out. So let's get the maximum moment. We can say taking moment about point B to be 0. We can have AY times. Instead of taking each of the load one by one by getting the total moment, we already have the resultant load act and we know where it's acting on, so we can easily get the moment with respect to AY. Okay, so let's say AY times 20, all right, and minus the resultant load, which is 5P, times, so this is here, which is 6.9. Let's find out what is left over from the resultant load. This is 6.9, all right. This one, this is 7.9. Uh, this is 6.9, this is 1, 7.9. 7.9 plus 2 will give you plus 0.2 will give you 8.1. 8.1 plus 9. So it means that our AY becomes 5P times 8.1 divided by 20. So if we do that, we are going to obtain a value for AY. And that will give us a value for AY as equal to 25 P kilonewton. That's all right. So we have the value for AY. So the next thing we're going to do is to determine the value for moment at these 2 points. That is the point P2 and point P3. Once we try it out, we'll find out which of them will produce the maximum moment for the beam. So now let's consider point A1, point 2 rather. If we do point 2, you will have that moment at point 2. Moment at point 2 will become 2.25 times 2.25 P, sorry, times from here to P2, which is 3 plus 5.1, which is 8.1. So we're going to have here to be 8.1. So if we multiply 2.3P times 8.1, that will give us a Fox value for moment at P2. If we do that, we're going to have the moment at P1, which is P1 times 3. Okay. So if we do that, we're going to have moment at point. All right. We can similarly also determine the moment at point 3. If we do the moment at point 3, we'll have it as moment at point 3 becomes equal to 2.025 times distance to point 3. What is the distance to point 3? This is our point 3. Remember this point 3. Okay. This point 3. So if here is point 3, what is the distance? The first one we have, this is our resultant load. This is what we have our resultant load. Let's draw here carefully so that we can see it clearly. Here's our P2. Okay. So if this is what we have, we'll have 10 plus 1, 10 plus 1.9, that will give us 11.9 plus 0.2 will give us 12.1. So we are saying that from support A to P3 is 12.1. So the moment becomes 2.025 times 12.1. And let's look for that of P1. So we have P1 times. Now let's look at distance to P3. Here is 3 meters, right? To P3 is 4. So we're going to have P1 times 7. Okay. The next we're going to have is P2. So we have P2 times, what is the distance to P3? The distance to P3 is 4. So we have times 4. All right. Then the next we have got to P2. I think that is the highest. So moment at point 3 becomes what it is. So we have the moment M3 to be 13.5025 P kilonewton meter. Now let's go over to the next stage. The next step is to determine the moment due to the second arrangement, load arrangement, as we have it on the board. All right, so let's go over to the next one. Quickly, let's draw the beam. We've seen it as this. Quickly, we'll try and get the distance here. This 3, this 10 meters, span of 10 meters. So if we have 10, yes, 3, yes, 3, 6.8 rather. All right, 6.8 plus 0.1. That will give us 6.9. So we'll say 10 minus 6.9. That'll give us 3.1. So here is 3.1. Okay, so we have here to be 3.1. So 3.13 point 1. So everything will give us 10 at this point as the center line of this bin. So quickly, we needed also to get this other side, like we can see. If here 3.1, this here 0.1, 0.1. Okay, so here we'll have here to be what? 1, 9, which is 9.1 from here to where we have this load to be 9.1. So from here like this is 9.1 down to where we have this load. So if that is the case, it meaning here is going to be what? 0.9. All right. So like on the case of the first load where we have that the load P5 was found to be outside the support of the simply supported beam. This time around, we are having that the load P5 is already inside the simply supported beam, though it has moved a distance of 0.9 from the support. So as it is, we can easily get the moment. So summation of moment, calling here A, calling here B. Summation of moment about B equal to 0. We'll have AY times the resultant force is here. Remember, the resultant force is here. Okay, this is the resultant. All right, this is the resultant, and we know it is 5P. So we are saying this times what? Times 20 minus we have 5P times. Now, what is the distance of the resultant force? We have it as 1 to 8. So to give us 10.1 equal to 0. 50.5P over what? 20. That will give us our AY. All right. So if we have 50, but we've already gotten our AY. The next thing we are going to do, AY, we got AY to be 2.525P. Okay. So now the next thing we are going to do is determining the moments at each of the point. Of course, like we said in the other situation, in this case, the same thing it applies. The determination of maximum moment will be between P2 and P3. So we'll try them one after the other. So let's try P2. We will now have moment at P2, M2 will be 2.525P. Now let's take a distance to P2. All right. This 3.1, 6.1. So to P2, we have here to be 6.1. 6.1 minus the next thing we are going to check is to P2, we'll have a P1. Distance to P2 is 3. All right, it's 3. So when we do that, we're going to have M2 to become 3, 2.564.025P minus 3, 3P. So from minus 3 from this, we'll have 12.40P kilonewton meters. Okay, so that is the moment at point 2. All right, now the next thing we are going to check out for is to get moment at point 3. All right, so let's get moment at point 3. Moment at point 3 is equal to AY, which is 2.525P times distance to point 3. The distance to point 3 now becomes, this is our point 3, this is our point 3. So is 10. So we're having 10.1. So 10.1, 2.3. So we are going to have three load, 1, 2. So load 1 becomes P1. P1 distance of 0.3 becomes 6. And okay, let's just take it. Yes, 3 here is 4. So becomes 7. So we have P1 times 7 minus. The next one is P2. So it becomes P2 times 4. So P2 times 4. So moment at point 3 is uh, 2.525 times 10.1. So say 2.525 times 10.1 minus 7 minus 4. That gives us 11.77 p kilonewton meters. All right. Okay. So now we've seen two various load arrangements for determining the maximum moment for this particular beam due to this series of concentrated moving load. And we've discovered that from the two positions of the load, the first position will take precedence in terms of the maximum moment, and that position will be at under the load point, load P3, to be under the load P3, and we are going to have it as 13 point what 13.5. So it will take place under that load P3, and we are having it as 13.5025 p kilonewton meters. So that is the maximum moment of this series of concentrated load on this beam. So in conclusion, we can therefore say that the maximum moment of the load, since M3, let's call it M3 prime. Let's call this one M2 prime. Okay. So we can just say that M3, since M3 prime, M3 prime is greater than M2, therefore, since M3 prime is greater than M2, therefore, the first load arrangement, let's call it arrangement 1, takes precedence. So the maximum moment of this set of concentrated load on a this simply supported beam of 20 meters span, we can have it as 13.502 5p. It becomes the maximum moment of this particular beam. All right. So with what we have done today, I believe you'll be able to determine the maximum moment of a set of concentrated load of span, of any span. Even if the load is unsymmetrical, you can determine that conveniently. Now, in our next video, we are going to be dealing with influence line to determine the moment at any point along the beam when you have set of concentrated load moving on a simply supported beam. Thank you for watching. Please do well to subscribe and stay cool.